Okay, so as we've been hearing this morning, multicellularity evolved a number of times in the Precambrian in various groups of algae and cyanobacteria. However, the origin of multicellular animals and their rapid diversification around the start of the Phanerozoic is widely considered to be one of the most important events in the history of life. And there's a major mismatch between molecular clocks and the fossil record regarding the timing of this event. So molecular clocks suggest that animals began to diversify in the Cryogenian and through the Ediacaran. But interpretations of fossils from before the base of the Cambrian as animals are controversial. So a number of forms, for example, from the classical Ediacaran biota have been interpreted as animals, but these interpretations continue to be debated. Another important source of candidate animals from this time are the microfossils from the Doushantuo biota from the Ediacaran of southern China. In recent years, many of these fossils, both embryonic and adults, have also been called into question by other workers. And so many of these must also now be thought of as contentious. So this leaves a suite of tubular fossils from Doushantuo as perhaps some of the most widely accepted evidence for animals at this time. So these are a suite of 4 genera, which are distinguished from one another mainly based on their branching patterns, their overall form, and nature of internal crosswalls which they have. And these have been interpreted as eumetazoans with a body plan comparable to that of tabulate corals. But there are some other possibilities that which we should consider, such as whether the relatively simple structures in these fossils could be produced either by algae or by cyanobacteria. And so what I wanted to do was to characterize these fossils in more detail to try and see if we could identify features which would allow us to provide a test between these different hypotheses of affinity. And so, like Betty, I used Synchrotron tomography at the Swiss light source, which allowed me to characterize the fossils 3-dimensionally and a submicron resolution. And the first thing that I was interested in was whether these organisms were mineralized when they were alive. And the previous view is that they were soft-bodied, and the evidence for this is that some of the specimens are twisted and deformed. And while some others have brittle fracture, this was thought to have occurred later after they'd been fossilized. So what I did was to look at each of the 4 genera individually. So when I looked at this first one, Sinocyclocyclicus, and I virtually cut it open and zoomed in here and here, what we see is that there's lots of evidence for brittle fracture of the crosswalls. And this is true both of the complete crosswalls, which cut all the way across the tube, and also the incomplete crosswalls, which just come part of the way in. So both have evidence for brittle fracture. I looked at this next genus, Quadratitubus. This differs from the last one just in having a square rather than a round cross-section. And again, I found a similar pattern, brittle deformation and fracture of the complete and incomplete crosswalls. However, in this genus, Ramitubus, this is the only one of these taxa which branches, found a rather different pattern. Here we've got lots of evidence for ductile deformation. So we can see some in the external morphology of this right-hand specimen here. And when we look inside, we also see evidence for ductile deformation of the crosswalls. And another feature which we see in this genus, which we don't see in the previous 2, is evidence for for organic decay. So here the cross walls have decayed away, and the space between them has been filled by cement. And in the final genus, Crassitubus, we also see a similar pattern. And here, some of the specimens can even be completely twisted and knotted up like this one here. So to summarize, there's lots of brittle deformation and fracture in the first two genera, whereas this isn't present in the last two, which have evidence for ductile deformation and for organic decay. And because these fossils all come from the same unit of the Doushantuo, it's hard to envisage how the differences could be due to having different diagenetic or geological histories. So the best explanation is that the first two genera, Sinocyclocyclicus and Quadratitubus, were mineralized at least enough to undergo brittle fracture when they were alive, whereas the second two were not. So now I'm going to show some specimens which provide new information about the anatomy and construction of these taxa. So firstly, this specimen of Sinocyclocyclicus shows a whole load of faceted structures which fill the spaces in between the cross walls. And we can take another look at these if we take a transverse section through the tube. Next, there's a specimen of Ramitubus. So if we look inside here, we can see that after it branches, the nature of the cross walls changes. If we zoom in, we can see that in these regions, the spaces between the cross walls are filled with multiple layered structures. And another interesting aspect of this specimen, which we can see more clearly in this slice, is that towards the end of each of the branches, there's these roughly spherical structures. And these are now filled with cement. But their similar size and shape and position within each branch suggests that it's possible that they might have had a biological origin. And this next specimen of Crassitubus provides a clue to what that origin might have been. So here we can see a similar structure of a similar size in a similar position in the tube. And when we zoom in on it, we can see that it's composed of hundreds or thousands of cell-like structures. So it's possible that this might represent a dispersal structure in the life cycle of these organisms. But coming back then to these structures between the cross walls of the taxa, what could these be? Well, one possibility is that they might be cells. So we have algal cells preserved from the same deposit. And we can see that they're preserved in a similar way in this dark, low X-ray attenuation phase. And they're broadly comparable in terms of their size and shape and so on. And so that's one possibility. And another possibility is that they might be organelles or other subcellular structures. And there's some possible explanations here. And so far, we haven't been able to come up with a definitive test to distinguish between these competing hypotheses. But one that I think that we can rule out is that the tubes have become infested by bacteria. Firstly, in these experiments by Rudy Raff and colleagues, we see that bacteria can digest and completely replicate cellular tissue. But when this happens, even when they're really closely packed together like this, the individual bacteria retain their rounded morphology, and they don't become faceted like we see in these fossils. Also, this explanation couldn't account for the organized layered structures which we see in Ramitubus. Oh, sorry. So what then are the implications of all this for testing between these hypotheses of affinity for the fossils? So the possibility that these are cyanobacteria provides a neat solution or a neat explanation to the incomplete cross walls. So under this model, the complete cross walls would represent the boundaries between cells, and the incomplete cross walls would represent incipient boundaries which are forming as the cells divide. However, there's a number of reasons for which we can dismiss this idea. Firstly, the fossils they're an order of magnitude larger than the largest living cyanobacteria. Secondly, it's hard to explain why we only ever see alternating incomplete and complete cross walls in Sinocyclocyclicus, for example, and why we never see ones where division has completely taken place. And perhaps more importantly, it's very hard to see how this can be reconciled with the lightly mineralized nature of these incomplete cross walls. And finally, evidence for growth by this kind of intercalation is incompatible with evidence that we have in some of the taxa, especially the branching ones, for terminal growth. So the next model is that they might be eumetazoans with a body plan comparable to that of tabulate corals. So under this model, the spaces between the cross walls would represent the former living positions of the polyp. The polyp always lives in the space after the most recently added cross wall. So we'd expect these spaces either to be empty or, as we can see here, to be filled with diagenetic cement. And the presence, as was observed, of anatomical structures within these spaces is incompatible with this model. And that's true whether we interpret these structures as cellular features or whether we interpret them as subcellular features. Both are incompatible. So this removes the evidence which has been used to place these fossils within animals. But is it possible that they could be some other kind of animal? Well, this seems very unlikely because animals with complete cross walls tend to have a similar sort of pattern of growth to what we see here, where the organism lives in the final chamber. So, for example, this is what we see in cephalopods. So, based on the evidence we have, the best interpretation we think of these specimens is that there's some kind of eukaryotic alga. And there are broadly similar modern analogues, whether we interpret the structures between the cross walls as subcellular here or as cellular here. Although it's difficult at this stage to pinpoint the position of these fossils to any particular clade of algae. To summarize then, the fossils have features which are incompatible with an interpretation either as cyanobacteria or as animals. On the basis of the available evidence, the best interpretation is that they're some kind of eukaryotic alga. And so as a result, none of the fossils from this time can now be undisputably interpreted as animals, which means that this mismatch between molecular clocks and the fossil record persists for the time being. But we're getting an ever improved understanding of Ediacaran fossils, and this is going to help us get a better understanding of the events in the lead-up to the explosive radiation of animal fossils around the base of the Cambrian. Thank you very much, and thank you to all these people.